Hey guys, so today we're going to be coding a neural network from scratch, not using TensorFlow or PyTorch, just pure NumPy, and very simple neural network, but I think it's still a great exercise to learn how they work. All right, so let's start building. First thing we need is to import NumPy. We're creating the input and the output array. Now, what is the problem we're trying to solve here? It's a classification problem. A very simple one is the XOR, where we need to find, the output based on these two numbers, which are both Boolean. So it's either 0 or 1. Now, the output is equal to 0 if the input, they are both equal to 0 or both equal to 1. If they are both different, then it's 1. So very simple problem, but it cannot be solved in a linear way. That's why we are going to be using a neural network. Very simple one, but it's good to get our hands dirty. So let's get started by defining the architecture of our neural network. So we first need to determine the input size. Now in our case, it's 2 because we have only two numbers here in the input. Then the hidden layer size, let's say it's 4. We're only going to have 4 neurons, very small neural network, just to understand its inner workings. And then the output size, it's going to be 1 because we're only having this classification problem where it's either 0 or 1, just one number in the output. All right, next thing we need is our weights and biases. So let's initialize them. First, it's gonna be a random number. So we can use random from NumPy. And then what are the dimensions? The dimensions are input size and then the hidden size. Because the first layer takes as input, well, the input size, so it's 2, and then there are 4 neurons to take into account, so that's the hidden size part. And then the bias for this one, let's just make it a bunch of zeros because we're just initializing it. And then because they are not different in terms of input, there's only one in this dimension, and then the other dimension is the hidden size. And then same thing for the second part, except that here, because the input is the output of the first layer, this is going to be the input, and then here it's going to be the size of the output, and also here. So this gives us our weights and biases. We've initialized them. Now the next step is to create our activation function. We're gonna go with a sigmoid here. Very simple function. We can write it in just one line basically. It's 1 over 1 plus exponential of minus that. All right. And then we are also going to need the derivative of this function. So let's call it a sigmoid deriv in terms of a. Then we return a times 1 minus a. Now, next step is the training loop. Now, the training loop is one of the most important parts that we need to understand when we're building a neural network. This is the part that will really help us understand like the mechanics. But the mechanics behind a neural network essentially are you sort of make predictions, you see how wrong you were, and then you try to adapt all the inner weights and biases inside the neural network to get a little bit closer to the target. So first thing we need is a learning rate. Learning rate is how fast you adapt or how sensitive you are to those changes. Now, the more sensitive you are, the faster you might get the results. but also the higher the risk that you'll never converge, they'll never get to results because you're always changing and adapting your results. Now, next thing is the number of epochs. The number of epochs is basically the number of rounds that we're going to do that for. I think for these, we should try 10,000 epochs. I think it's probably more than enough. Now, we are going to run a for loop. So for each epoch in the number of epochs we've decided on, we're going to do this. First, it's called a forward pass. So the forward pass is making predictions based on our weights. So the first layer will take, and we are using a sigmoid activation function that we've created in the cell above. It's gonna be just the input matrix, and then you multiply, and this operator is the matrix multiplication operator by the weights, and then you add the biases, and that's it. That's our hidden layer. Now the output layer, it's gonna also use a sigmoid function, but it's gonna take the output of the first layer, and then it's gonna multiply it by the weight of the second layer and add the bias of the second layer. And that's it. That's your forward pass. Now, the second step is the backpropagation, which is essentially computing gradients. Now, the gradients will be, the adaptations to the results that we have. So because it's the backpropagation, it means we start on the output layer and then we go backwards, the opposite of the forward pass. So this one is going to be A2, so essentially the output that we had minus the actual results, the actual values we had in our data, times, and then that's where we use a sigmoid derivative for A2. And then for the gradient of A1, we're going to use the gradient from A2 times the weight matrix, transpose it, and then we multiply it by the sigmoid derivative of A1. This is going to give us the gradients, and then we use these gradients to update parameters. So the second weight matrix, we are essentially gonna take it and then subtract the learning rate multiplied by the results of the first layer transposed multiplied by the gradient A2. And then for the bias, we also subtract learning rate, but the learning rate this time is multiplied by the sum of the second gradient over the axis, over the first axis. And then we want to keep our dimensions. And then this is for the second weight, and then for the first weights and biases, it's essentially the same thing, except that here, instead of A1, we are using the input directly, the input data. And then here, it's the gradient from A1 and also here. And that's it. That should be our training. And if we run it, it should not take long. There you go, 10,000 epochs, but it's a very small network, so we're done with it in less than a second. Now, to get our predictions, first we take our input data, we multiply it by the first weights, and then we add the bias for the first layer. This is our first layer. we use our activation function, which is a sigmoid, and that's the output for the first layer. Now we need to take all of these and multiply by the second weight matrix. So essentially we're taking the output from the first layer and sending it to the second layer. Then we sum the second biases and we apply sigmoid over all of these. And these should be our output, at least in terms of probabilities, let's say. But because we want either 0 or 1, we can check if this is over 0.5. If so, then it's 1. If not, then it's 0. And then we can get our predictions as type int. So we're going to take true or false, and then we're going to turn it into zeros and ones. And there you go. You can see it was capable of predicting the XOR function very simply. It gives us an idea of how to multiply the weight, how to add the biases, and some of the interesting next steps for this is, I think, it would be to try other different activation functions, to add more layers, maybe to create a sort of a class or framework to automate the creation of those layers and so on. That's it, and I hope you liked it and keep on building.